Welcome to this brief introduction to RayJack ONE. RayJack ONE is a non-sequential ray tracer ideally suited for the design of illumination optics and for optical analysis, including, for instance, stray light analysis. I am Bernhard Mickel, founder and CEO of Hembach Photonik. In the next minutes, I would like to demonstrate how simple it is to set up an optical system in RayJack ONE and to perform a ray tracing simulation. RayJack ONE offers a powerful graphical user interface, but one of its key selling points is the Python scripting environment, which has intimate access to the simulation kernel of the software. Therefore, when we now start with setting up a system, we shall use a script editor. And when I enter here a capital B, auto-completion will make suggestions. I will select basic analysis script and press enter. It will create a header for the script, and you should take your time to fill it out, plus some initialization. To speed up a little bit, let me open a filled out header here. And the key command you see here is simulation split, which makes some initial settings. I set here the maximum number of splits to 2, and you will see the meaning in a few minutes. Python is an object-oriented language, and this means that any kinds of entities relevant for optical simulations like surfaces, media, coatings, BSDFs are represented as variables. And to create a lens, I can directly assign it to a variable. When I enter here a capital L, autocomplete suggests a lens. Pressing a dot gives me a sub option. Here I use a singlet lens. Another dot gives me a sub option, so that I can create here a singlet lens from its paraxial focal length. Now I'm prompted for parameters. Let me call the lens lens1. I specify the alignment along an axis. I choose the Z axis and put the left vertex at 0 millimeters. So we can use units and should do so, but the default units are millimeters anyway, so I could have left that away here. For the thickness, I use another technique, so-called keyword arguments, in order to make the script easily readable. Let me choose here 4 millimeters for the central thickness. For the semi-diameter, I select 11.5 millimeters. For the focal length, 50 millimeters. And let me continue on the next line. The bending factor, which tells me how the curvatures are distributed over the surfaces, is set to 0. And then I specify a design wavelength. Let me select 550 nanometers. And finally, the glass. In order to do that, I can define my own glass here, but I can also select a glass from the glass catalog. And for instance, when I select here a shot BK7, click on it, I see the dispersion curve, but I also can immediately drag it here onto the script so that my lens is now assigned shot BK7. In order to bring this system into the simulation kernel, I have to run the script by clicking here on this button. This tells me success here, and I can now have a look at the system by clicking here on the 2D profile view, or I can use here the 3D view, a tool which offers capabilities just like in a normal CAD program. Let me continue with a screen that catches the light from the lens. For this end, I now define a physical object, which is used for all surfaces with which rays can interact. And there is practically no surface type missing. If you find one, you can enter it yourself as a Python function. Here I simply select a plane, give it a name, I call it screen, align it as before along an axis, and let me choose now the position to be 52 millimeters, and for the aperture let me take again the keyword arguments. I use a square aperture with 5 millimeters semi-side length. Now when you look at that, you see it's immediately readable and self-explanatory. So it is as good as representing data in spreadsheet form, but you get additionally now the strength of a scripting language. Let me continue here with creating a light source, and it is as simple. Once again, I assign it to a variable, and a source is now of type source. Pressing a dot gives me a rich variety of light source types. I use a simple grid source and a collimated one. Opening the parentheses now prompts me for the arguments. I call it a laser and specify the axis again, the position. Let me place it 1 millimeter in front of the lens. The aperture, for which I take a circle, slightly smaller than the aperture of the lens. And now I have to specify the direction. Now I will do that in 2 steps. Here, when I say direction, I choose the name of a variable. And the same for the height, the number of rays in height and width direction. Numbers of rays. Height direction, let's use a variable here, and ray. The same for the numbers of rays in width direction and ray. And finally, I have to specify the wavelength because we have a dispersive class. So it's necessary to know that. When I run this script, it will cause an error because we have not specified what the direction is. The direction is a vector in 3D, and this is represented by a variable of type vector 3D. So I could use something like 1, 2, 3, but here it's more appropriate to specify the direction through polar coordinates, the length of the vector, which is inconsequential, the polar angle, for which I choose 3 degrees. So we allow for angular units, degrees, radians, and others. And now for the azimuth, I use 90 degrees. So the direction is done. Still, I have to specify the number of rays in both directions. And let me use 31. So when I now run this script again, it should show me the system. So the light source is represented as a gray plane. Here we have the screen. And now let's go on with ray tracing. I simply click here on this button, and you see it will immediately perform the ray trace. You see more rays than you might have expected This is due to the fact that we have allowed for double reflections of the rays inside the lens. This is specified here in this simulation split command. If I set this value to 0, then I will see only the nominal light. Let me trace again, and then you see just what you would have expected normally. Let me go back here to 2 and show you another trick. So instead of clicking on buttons, you can do everything, including graphics, inside the script. So once again, it's advisable to create a variable. And now I assign to the variable a system view. This will create something like that, the view of the system. Also, when I want to trace the rays, I can create a ray tracer object. A ray tracer dot, and then I have a selection between different types of ray tracers. I will take the non-sequential ray tracer, give it a name, tracer, and now I may assign the viewer to this ray tracer. If I don't do that, it will create its own viewer. And finally, I will trace the rays by launching the ray tracer. So let me do some additional things here. So this would exactly reproduce now what you already have seen before, to show the advantage of using variables, because now I can set certain properties to the viewer. For instance, I may set the ray color. Let's use a color red, which would now color all the rays red, which is a little bit boring. But I now use the second parameter here, a so-called ray filter, to select out certain rays. Let me select the number of splits of the ray and set it to 2. This will color all rays that have been split twice in red color. Let me use copy and paste, use blue for the rays, and set the number of splits to 1. In this case, it will color all rays in blue color that have been split only once. Let's see what happens by clicking on Run. And you see now you have the ray trace done automatically, and the rays are colored according to their history, what happened to them. That's enough for this video. In follow-up videos, I will dive deeper into radiometry and analysis of optical systems.